Hello everyone. In this video we are going to talk about operational amplifiers or op-amps, which are common elements in electronics and controls. So the op-amps are basically small circuits like this, correct? A small chip, maybe most of the times with like 8 legs, and some of them have one, some of them have two op-amps in them, these chips. One of the very common one is called 741, op-amp 741. And inside of it, well, it's very complicated. This is not what we want to talk about today. And actually, it's a little bit beyond my specialty. But inside of it, you see transistors, you see capacitors, and you see resistors. And it's quite a bit complicated. So we are not going to have a microscopic view at it. We're going to look at the macroscopic, see outside of all the circuits, what is it that it's basically doing and how it can be used in controls. So the inputs, it has typically two inputs. This is like a schematic picture or diagram for an op-amp. So it has two inputs, E1 and E2, and it has this output EO. And the inputs or outputs could be AC or DC signals. And the output in an ideal, and we'll talk about ideal, in an ideal amplifier, the output is a constant, which we call differential gain, times the difference between the two input voltages. So E2 minus E1, the part that goes to the positive port, minus the one goes to the negative port, multiplied by a gain, a big gain typically, is the output voltage. So clearly you see that it is amplifying your voltage. That's why we call it amplifier. And it's a differential one because it amplifies the difference between the two input voltages. Now, this gain K here, which we call differential gain, or the op-amp gain, this is typically a large number as long as the input frequencies, the frequency of the input signals are low. So if they are like less than 10 hertz or so, typically it's like 100,000 to a million. It's a big gain. But as the frequency of the input signal goes up, this gain goes down and ultimately approaches like a single unit 1 when the frequencies are very high, like up to a megahertz or something, right? So the frequency, if you draw the gain K versus frequency, it is gonna drop to ultimately 1. So at high frequencies, basically it's not doing anything. At low frequencies, it's amplifying the voltage very large amounts. Now, in an ideal op-amp, we say that this is the relation between the input and output voltages, and we say that no current flows into the input terminals. Okay, so the currents here are very negligible. We just neglect them. We say that's 0. And the voltage that you get out of the output, it does not depend on how much load you apply here. Okay, so if you connect this to some load, and if this load is big or small or it's an impedance, let's just say Z of L in general, because it's not always a resistance, whether this load is small or big or how much it is, in an ideal one, we say this voltage is not gonna change. In reality, that's not the case. This output voltage does depend on the load, and there is very small current through the input terminals, but for analysis here, we go with the ideal op-amp assumption, okay? There are other things about ideal op-amp, like the noise and a bunch of other things, the disturbance rejection and so on, noise, input noise rejection and so on, but I don't want to get into those. Again, I'm not necessarily super expert in those areas anyways. So here we assume that the input impedance is like infinite and the output impedance is 0. And using these, we're going to analyze circuits that have what? That have op-amps in them, okay? For instance, a simple circuit you might look is this guy here, where basically the two signals that are going in, one of them you grounded it, so this signal is basically 0 voltage, and the other signal going in, on the way of it, you have this resistor and goes to the negative port, and then you have this branch coming out with another R2, another resistance, and goes to the output. And now you want to know what is the relation between EO and EI here. So first thing is, between these 2 points, we write the circuit, the KVL law, which says the difference between E prime, if you call the voltage at that node, if you call it between that point and the ground, basically this whole thing, if you call it E prime, EI minus E prime is R1 times I1, and I is the current in this line here, okay? And then you write it between E prime and EO here, right? So the EO minus E prime is going to be the current here, I2 times R2. So you can write I2 as the difference between those two voltages divided by R2. Now, as I said, the input currents into the terminals of op amps are very small. So here, this current, you see here I have a node. So I1 goes in, and then this I and this I2 go out. So I1 is equal to I plus I2. But this I that goes into the terminal is very, very small. We practically say it's approximately 0. That means I1 should be equal to what? I2. So all of this I1 goes to this branch I2. If that's the case, means these two ratios are equal. And the other thing about the E prime, the voltage at this point is, well, based on the law that we know, I just showed it up to you, based on this rule, what can I write for the relation between E prime and EO? Well, this voltage here, this E is 0, right? Because it's grounded. So 0 minus E prime, the difference between these two voltages, times the gain K is equal to EO, right? So this is that rule of that amplifier. Now, if we assume that the frequencies of the signals, the input signal EI, is not large, then this K is a big, big number, like as I showed you, 100,000, a million or something. If that's the case, it literally means this E prime is a very small voltage. Why? Because you see that E prime here is what? It's negative EO divided by K. And when K is very big, this E prime is practically close to what? 0. So here I get rid of these two E primes. So you get EI over R1 is negative EO over R2. So you get this equality, or if you write it, you see EO is a negative of a constant number times E2. So what relation exists between EI and EO? EO is a multiple of EI. That multiple could be bigger or smaller than 1, depending on the ratio of R2 and R1. And there is a negative sign. So the direction is opposite. The direction of voltage EO is opposite of EI, or in other words, we call it inverting op amp. If I make R2 and R1 to be the same resistor, then EO is exactly negative EI. So we call it what? Inverting op amp. So one of the things you can do with op amps is not only you can amplify the signal, right? You can basically invert it as well if you want to. But there is more than this simple thing that you can do, like amplifying or inverting. There are a lot more that you can do, and that comes when you bring in capacitors, and I'll show you. So as long as you just have resistors, it's typically a gain or an inverter or both of them, but when you bring capacitors, it makes it more interesting. And to be able to analyze it with capacitors and not go through the integral and derivative relations between current and voltage of a capacitor, we use the impedance approach. And for capacitors, you know, for a capacitor with capacitance C, the impedance is what? Is 1 over CS. So we use this approach, while for resistor R, the capacitance, the impedance is simply R, and for an inductor is L times S. So we use this approach, and using this approach, we can see that we can analyze op-amp circuits much easier. So let's say here, for instance, I have what? I have this circuit here, which is very similar to the previous circuit. If you look at it, instead of R2 and R1, I replace them with two impedances, Z2 and Z1. That's the exact same thing. And very similar to last time that I showed you, EO over EI was R2 over R1 with a negative sign. Here I can show you again, EO over EI is negative of this time Z2 over Z1. Okay, clearly you see the inverting relation and the relation of the two impedances. Okay, now how can I use this now that I got this important relation? So let's look at this circuit now. This is the circuit of an integrator, basically an I controller. Let's see what happens. So here, the main circuit is the one in green, where you replaced this R2 with a capacitor C2, and this next portion, all it does, this next portion is just inverting it. So the second portion in the blue is the inverter. It's this guy that is integrating. So you might say, why do you need that inverter? Because as you'll see, if I just integrate, not only it integrates, it's also multiplied by -1. So it integrates and invert. Okay? So if I add that other inverter, then that inverter and this inverter would cancel and the effect will be only integrating, which is what I want. So now, how do I basically analyze this? Well, if I look at the green circuit, the output voltage E3 over EI in the Laplace domain is going to be what? Negative of Z2 over Z1, where Z2 is this and Z1 is this. So Z1 is the same as R1. Z2 is 1 over C2S. That's Z2. And if I look at the blue circuit, then EO over EI, output over input again, E3, I'm sorry, is negative of R4 over R3. If you multiply the two sides of these equalities together, that E3 and this E3 would cancel. You get EO over EI, these two negatives would cancel, and so you get this relation here. And guess what it is? Well, if you look at this whole thing here, this whole thing is a simple constant, because R4, R1, R3, C2, they are all numbers. So this is like a simple number, which I might call it K or Ki, right, over what? As you can see, over S. So you see it's clearly what? An integrator. So this circuit is what? An integrator. So I can make an integrator if I want to, with an op-amp and a few resistors and one capacitor. Now, can I do other controllers? Sure. For example, if I want a PD, proportional derivative, if I want a PD op-amp, what can I do? Well, take a look here. This time, again, it has two portions. This portion is clearly the inverter, just to basically get rid of the inverting property of the first portion. Now, the first portion, which is this part, basically, this first portion, if you look, this time, instead of having the capacitor connected to output and resistor connected to input, you did the opposite. You brought the capacitor to the input side, you brought the resistor to the output side. But you don't just use the capacitor on the input, you combine it with the resistor in parallel and then connect it to input. So if you displace the location of or swap resistor and capacitor from input output, instead of integrating, now you're going to do derivative. So you might say, what is this R1 then for? Well, this is for the proportional part. This resistor capacitor does the derivative part. When you bring that R1, that does the effect of proportional part, and the second part, the negative of that will cancel the negative of this guy, so you'll get the whole effect. And you can see that analysis here on the right side. Let me clean up so you can see better. So for the first circuit, as I showed you, E3 over EI is negative of this impedance, which is R2, over the impedance equivalent of the parallel C and parallel R. Now, since they are parallel, the equivalent impedance is going to be Z1, Z2 over Z1 plus Z2. And you know, if you simplify this, what will you get? Well, you get R1 over what? Over 1 plus R1 C1S. Correct? Which is what you can see over here. So R2 over, or Z2 over Z1 with the negative sign, that's E3 over EI, and then EO over E3 is again negative R4 over R3. Multiply both sides together, get rid of E3s. EO over EI is going to be the product of these two, which is R2, R4, over what? R3 times what? R1, and then that's R1, that's R3, and then this term goes to the numerator. And if you look here, again, this is just a single number, right? So if I call it Kp, this guy is going to be like Kp times 1, which is Kp, and then plus Kp times this guy, and the product of that R1C1 and Kp, I can call it Ki times S. And you clearly see that what this is, sorry, Kd. I'm sorry, this is Kd, not Kp. Not Ki. Kp plus Kd times S, and this is what? This is basically your PD controller. So here is what? Here is the PD circuit. Correct? That's the PD, that's I, and if I combine, guess what? You're right. I can get a PID controller. So I can make PID controllers by what? By combining two what? Op amps, two resistors, and two capacitors. And the interesting part is this. What's different here compared to the two previous parts? This time you have capacitor both connected to the output and also one for the input. And resistor here is a series with capacitor, here is in parallel. So as you learned, this capacitor for that resistor is a D term, this resistor and that resistor is a P term, and this capacitor with that resistor is an I term. There is, of course, a negative, with the negative of the second stage would cancel. So this whole thing, if you simplify it, and you can do it if you want, this is going to be this guy here. And it's not hard again, right? All you need is to say how much is Z2, how much is Z1. Here, your Z1, as we calculated last time, it was R1 over 1 plus R1 C1S, and Z2 here, since these two are just added together, it's going to be R2 plus 1 over C2S. Or if you write it, it is going to be 1 plus R2 C2S over C2S. And these two terms, that denominator and that one, are what you can see in here, the numerator. And then basically that C2S multiplied by R2 is what you can see in this denominator. And if you look at here, clearly you see if you multiply these two together, you get like 1 plus, and then R1 C1 plus R2 C2, the whole thing times S, and then plus R1 R2 C1 C2 S squared. This whole thing over that constant, you can just call it K. There is S here, right? And then again, you can call these guys some other things. So maybe that one you call it K1, this guy you call it K2, and this whole thing you might call it K3. So it is going to be like K1 and then plus K1 K2S and then plus K1 K3 S squared, the whole thing divided by S. And clearly here you can see that this is your integrator, and this part here is your constants proportional, and this last portion here is your derivative. Okay, so you have what? You have a PID controller. So here is what? Here was PID. Okay, you might say, can I make compensators also? The answer is sure, you can make compensators. So here are the circuit for compensators. If you look at them, on the top you have lead or lag, where you can see here the difference is this time you brought that capacitor of the output and that resistor, you made them as well parallel like the input. So the only difference is compared to a PID here, R and C of the output here were series, this one was parallel, now both of them are parallel. And if you do that, you get a lead or lag, and again, you clearly can see this is like a gain, and these are those linear term in the numerator and denominator. Depending on which one is bigger, you can have lead or lag, right? Whether R1C1 is bigger or R2C2. And lead lag is when you have both of them, and for that, what you need to add is an extra resistor here compared to the lead or lag only. An extra series resistor to C2 you add here, and here also an extra series resistor to C1 you add. And if you do that, now you can see is clearly what is clearly a lead lag, right? Because you have the constant, and then here is one linear term multiplied by another linear term divided by the product of two other linear terms. So clearly it's like the product of a lead and a lag, which you call it lead lag. So here are all different circuits that we learn in basic controls, PID, lead lag, inverting, and so on. And you see all of them can be done with this amazing powerful tool or circuit called an op-amp, and with a bunch of resistors and capacitors. So hopefully it was useful to you, and I'll see you in the next video. Thank you.